This is chapter 8.1, exercises 59 through 64, and this is again section 8.1 in chapter 8. And this has to do with exercise set, and this is toward the back. We've gone through problems 1 through 20 in the previous video lessons. Here we're going to the back of the set, which deals with real engineering problems. And so this is really one of my favorite parts of the pre-calculus curriculum right now. Designing a flashlight mirror. A mirror of a flashlight is a paraboloid of revolution. Its diameter is 6 centimeters and its depth is 2 centimeters. How far from the vertex should the filament of the light bulb be placed for the flashlight to have its beam run parallel to the axis of its mirror? So what we're looking at right here is if we have a paraboloid of revolution, which I'm going to draw like this. Okay, we have the vertex here at the origin and comes up like this, and I think on the left side. So that's a rough paraboloid of revolution, and we have its diameter of 6 centimeters. So we'll say across here, this is going to be 6 centimeters across here in blue, and its depth is 2 centimeters. So here, this is 2 centimeters. Right here, how far from the vertex should the filament of the light bulb be placed for the flashlight to have its beam run parallel? So what we're having is we're having a beam from a filament here, somewhere in the center, will come out and hit this satellite dish, go out this way and run parallel. So let's get a coordinate pair. And if we're starting here at the vertex at 0, 0, what do we have up here? Well, we're going up 2, so we have comma 2, but what is our first value going to be? Well, it's going to be 1/2 of this 6. So we're looking at the value 3, 2. So we're going to be using these numbers, x equals 3 and y equals 2, to find the equation of a parabola. And from that, we're going to be able to find the focus. So let's do that. The equation form we have is y equals ax squared. Okay, so we got to really find what a is. We have these values here, 3 and 2. So y, which is going to be our 2, right? This is where we get that 2, equals a times x squared. Well, so it's going to be our x 3 squared. So anyway, that's where all that comes from. I'm going to erase just to give room to work below. Now, what we have is 2 is equal to 9. 3 times 3 squared is 9. 9a. And so if we divide by 9, we have a is equal to 2/9. Okay, so that's going to be our a. So we go from a equals 2/9. Now I'm going to arrow to the right here, so we say y is equal to a, which is 2/9 x squared. Now, we're going to use the form, what we call the standard form at the beginning of the lesson, which I really call the focal length form, which is going to be x squared equals 4py. Okay, this is what it's called. They call it the standard form. I call it focal length form. And by focal length form, I mean that 4p is the focal length. And to do this, we need to solve for this equation above for x squared. So to get this in standard form, if we take, I'm going to write this down below, y equals 2/9 x squared. We need to solve for x squared to get this in the focal length form, and so we're going to multiply. How do we get rid of this 2/9? We multiply by its reciprocal. So we multiply by 9/2, the left side and also the right side. Now, so we have on the right, left side and right side. So on the right side, 2/9 times 9/2, they cancel each other. So we have left x squared equals 9/2 y. Well, in focal length form, this 4p is in the place of, I'm going to just draw the arrows here, in the place of this 9/2. So we put 4p equals 9/2. And p is our focal length. So if we, how do we get p by itself? We divide by 4. And on the right side, if we divide by 4, that's putting the 4 down in the denominator. So we have p equals 9/8. 9/8. So that's going to be 9/8 centimeters. Equals 9/8 centimeters. So verbalizing, just looking at this value where the filament needs to be placed is going to be 9/8 of a centimeter. I'm just going to write this. Here's where our filament is placed, and this distance here, okay, this distance here is 9/8 of a centimeter. So I guess 1 and our mixed number would be 1 and 1/8. So just to verbalize this, we'll say the filament should be placed (9/8) or 1 and 1/8 from the vertex. So a little bit of work here. First to find the equation of our parabola, then to use that equation of parabola to find the focus of the parabola. So let's go on our next odd number problem, which is 61. Parabolic microphones. The sports channel uses a parabolic microphone to capture all the sounds from golf tournaments throughout the season. If one of its microphones has a parabolic surface generated by the parabola x squared equals 10y, locate the focus, the electronic receiver of the parabola. And again, what we're looking at is similar to the last problem we looked at, 59. This one here, they give us the equation. We don't have to find the equation because they give us the equation. And here we have a parabola like we had last time, and we have the equation of the parabola. We're trying to find again where to place, in this case, the receiver, okay, which I'm marking the blue dot here. Okay, so x squared equals 10y, and our standard form is going to be again x squared equals 4py. So using the standard form, we equate this 10 with the 4p. So these values, 10 and 4p, we can set equal to each other. So we put down here 4p is equal to 10. And we divide by 4 to solve for p. P is, of course, our focus. So 10/4, which simplifies to 5/2, or if we decimalize this, it would be 2.5. And again, the units, doesn't give the size, does it? It doesn't say if this is inches. We'll say units from vertex. and the focal width is going to be 10 across. So this is going to be, focal width will be 10 horizontally here, and this distance here is going to be 2.5 units. So this one was a lot easier, I felt, than problem 59 in that we were already given an equation. Let's go to problem number 63, which is designing a suspension bridge. Kind of an engineering problem. The main cables of the suspension bridge uniformly distribute the weight of the bridge in the form of a parabola. The main cables of the Precalculus bridge are attached to towers that are 600 feet apart. The cables are attached to towers at a height of 110 feet above the roadway and are 10 feet above the roadway at their lowest points. The vertical support cables are 50-foot intervals along the, if vertical support cables are 50 feet intervals along the roadway, what are the lengths of these vertical cables? So they give us a lot of information here. One, and I'm going to go ahead and draw this here kind of at the lower left, we have a level roadway. So I'm going to attempt to draw here a level roadway. And then we have two towers. The two towers, I'm going to go ahead and make them, they're 600 feet apart and at a height of 110 feet above the roadway. So these towers here, I'm going to call 110 feet high. And these are 600 feet apart. So 110 feet is the height of these towers. And there's a parabola that stretches, that spans between these towers and gets 10 feet to a low point at their lowest points. Okay, so 10 feet. So if we go down here, we're going to come, go a little steeper like this. And so at the lowest point, these are 10 feet above the roadway. We have, so this distance here from the lowest point of the parabola to the level roadway is 10 feet. And the cables are 50-foot intervals apart. So I'm going to mark those because if we have 0 here and if we have 50 feet apart, we're probably going to have 6. Mark these in green. Okay, this would be 50 feet because this is 600 feet apart, right? So 600 feet from here at the right to here at the left. And so span 600 feet, we'll have 50, 100, 150, 200, 250, 300. So I'll mark these 100 feet, 200. And what I'm going to do is I'm going to actually change this because I'm going to consider this a parabola. And to do that, I'm going to start right at the center. And starting right at the center, I'm going to call this 0, like our vertex right here, 0, 0. Then this will be negative 100 here, 2 spans to the left, negative 200, and negative 300 right at that left tower. And on the right side, we have 100 here, which is 2 cables over, 150, 200, another 2 cables over, and finally 300 feet right here. So this meets the requirement of these cables being 50 feet apart. Now I'm going to draw in purple, extend these cables from the level roadway to the cable of the bridge, this blue arc. So here we have our now to the right side of the lowest point. So these are going to be our cables. We need to find what are the lengths of these vertical cables. All right. So really an engineering problem. To do that, we're going to need to find our equation for our parabola. And to do that, we have our vertex down here. And I'm going to, in finding the equation of parabola, we could do if we wanted to, we could do a quadratic regression in our calculator, given this point at the upper right, this point at the upper left, and the vertex. We're going to do this without a parabola, and I'm going to go, we'll consider the equation of this parabola here starting, now we're 10 feet above bridge level here at the lowest point of the parabola, and we're 110 feet. So this distance up here from the lowest point of the parabola up to the top of the tower is going to be 100 feet. And the sideways distance is going to be half of 600 feet, which is 300 feet. And so our coordinate here, our XY coordinate, is going to be 300 to the right and 100 up. So we have 300, 100, that's considering our vertex 0, 0 is right at the lowest point of this parabola. So we have y equals ax squared. We can plug in for y 100, and we can plug in for x 300, and so I'm just going to bring this below. We have let's see, y, we have 100 equals a times 300 squared, right, ax squared. So that's going to be 100 equals 300 squared is 90,000. So we have 100 equals 90,000. A, if we divide both sides of this equation by 90,000, we're going to have solved for A. We'll have our equation of a parabola, so that's 90,000. And 90,000 over 90,000 cancel. We cancel a couple zeros. What do we have left? 1 over 900. So A is equal to 1 over 900. So therefore, our equation for our bridge, for the parabola, is going to be y equals 1 over 900 x squared. And what we're doing, since we're raising this parabola up by 10, we're going to add 10 to this equation. So for the lengths of cable, we already know, and I'm going to write the lengths below here. This will be 10 feet. We know that. In fact, I'm going to do the little foot hash markings. I'm going to put the little apostrophe there to represent feet. Next, for 50 feet over, we're going to use this equation. I'm going to go to my calculator. We're going to go 50 feet. And to do that, we're going to take, I'm going to take 50 storage x. So we've stored x for 50. And so our equation of parabola is going to be 1 over 900 times 50. I'll say x squared, right? I said that was x. Let's go back. X squared plus 10. And this will be our cable length for 50, so that's 115 over 9, and to decimalize, 12, we'll say to the nearest tenth of a foot, 12.8 feet. 12.8 feet. So we go back to our drawing and we say, okay, let's get this here. Okay, 12.8 feet. And that'll be this cable here. And symmetry also says it'll be this cable here to the negative 50 feet. Okay, so we get one cable of 10 feet, two of 12.8 feet. Next thing we're going to do is go to our calculator and put in 100. Storage X, and then we just type in the same we did before, control 1/900th, and we have x squared plus 10. This pen is sticking on me, so I'm okay. Oops, I put 110. I wanted just 10. All right, there we go. And for that, we get 190 over 9, which is decimalized going to be, I will say 21.1 feet. So we go back here. So this one, we'll say 21.1 feet. And that's also going to take care of this one at negative 100 because of symmetry. And so next, we're going to go to 150. 150 storage X. Okay, and then we type in 1/900th. X squared plus 10. We get 35 feet, so that's our next one at 110 feet. So that's going to be this one here. I'm going to write up above, kind of out of room, 35 feet. Okay, and then this one here at negative 110 is negative 150. That's also going to be 35-foot length cable. Next we go to 200 feet from the center. Oops, 200 feet from the center, so 200. We only have two such calculations to make now. Control X, and we put in again 1/900th. We have x squared plus 10. Okay, we get 490 over 9, which decimalized gives us 54.4 feet above the roadway. So this one, 200, we'll say 54.4 feet. And that's going to be also this cable length at negative 200 feet. And we just have one more length of cable to calculate, this one at 250 feet and at negative 250 feet. And to do that, we're going to put in 250 storage X and enter. And so we put in 1/900, excuse me. X squared plus 10. So we get 715 over 9. Control. Oops. What did I do? What did I do? Control. No syntax. I have to re-enter it. put a 1, 900th, x squared plus 10. That's having stored 250. Okay, control, enter. There we go, 79.4 feet. So we're going back to our drawing. This cable length here will be 79.4 feet. And so that will cover this cable over here, negative 250 feet as well. So we have all these lengths of cable, engineering problem, and those will be our answers. Good luck on the even number problems. To me, this is really an interesting problem set where you can visualize real-world uses for the conics. And I thank you for viewing.